Getting the desired products from any distillation system depends on operating the system properly. It also depends on recognizing problems when and if they occur, and knowing how to correct them. In this program, we're going to take a look at the operation of a typical distillation system. We'll begin with the procedures for starting up a distillation column. Then we'll look at the procedures for operating it properly. We'll also examine some of the problems you might encounter during startup and operation and what you can do about them. Finally, we'll see the procedures for shutting down the system whenever it's necessary to do so. Let's begin by looking at this graphics board. This graphics board is a representation of the distillation system we're going to be starting up and operating. Throughout this program, we're going to refer to this board. So when we talk about the reboiler, for example, you'll be able to see exactly where the reboiler fits in the entire system. When we mention the level indicator on the overhead product recovery tank, you'll know just which one we're talking about. There is one thing, though, that you should keep in mind. This board and the distillation system it represents are for this facility specifically. It's a typical setup, and the one at your facility may be very similar. However, there may also be some differences between this system and the one you work with, even though the basics are the same. Of course, you will follow your own system's procedures if ours are different, but you will still benefit from a knowledge of basic operations when operating your system. Okay, let's go back to the board and briefly review the distillation process to see how this system is set up. The liquid mixture to be distilled is held in this feed tank. It's a binary mixture, which means there are two components to be separated. First, the mixture is pumped to the preheater. The preheater raises the temperature of the mixture to its boiling point. Leaving the preheater, the mixture goes into the distillation column, where the two components of the mixture begin to separate. The heavier component of the mixture, known as the bottoms product, collects at the bottom of the column. During distillation, this bottoms product is constantly recirculated through a reboiler and back into the column. The reboiler reheats the bottoms product. Recirculating the bottoms product through the reboiler supplies enough heat to the column to complete desired separation of the mixture in the column. When pure enough to meet product specifications, the bottoms product will be drawn off. Meanwhile, the lighter component, known as the overhead product, rises to the top of the column as a vapor. This vapor is routed to a condenser, which cools the vapor and turns it back into a liquid. The liquid is returned to the column as reflux. Once the overhead product is pure enough to meet product specifications, a portion of it is pumped to the overhead product recovery tank. This system operates under a partial vacuum. A pair of steam jets is used to create that vacuum. As the jet steam is condensed, it flows to the condensate hot well tank. Well, that's how this distillation process is set up. For the next few minutes, we're going to talk about the startup procedure. The startup procedure for this column requires two people. The first, whom we call the inside operator, works in the control room. He's responsible for the overall operation of the distillation process. He monitors the system instruments and relays information to the other person, called the outside operator. He works at the column. He acts as the legs for the inside man, operating valves and other pieces of equipment needed to bring the column into operation. These two operators communicate with each other either by two-way radio or by the PA system. Engineers have set down the guidelines for starting up and operating this distillation system. It's the responsibility of the people who work at the column to make sure the guidelines are followed. Okay, let's take a look at the startup procedure. The operators begin by performing a series of pre-startup checks to make sure that all the necessary systems and equipment are operational. For example, they need to make sure that all the valves that are supposed to be closed are closed, and all the valves that are supposed to be open are open. During the pre-startup inspection, the outside operator will check all the equipment on the ground level first. Then he'll move up to the next level and check everything there. He'll continue this procedure all the way up the column to avoid continually running up and down stairs. To begin with, the outside operator checks to make sure that the drain under the overhead product recovery tank is closed. This prevents any loss of product during the startup. Next, he selects which recirculating pump will be used. Typically, recirculating systems like this have two pumps. However, only one pump is used at a time. So facilities typically set up some sort of system that determines when one pump of a pair will be used. And because only one pump is used at a time, this enables the pump not in use to always be available as a standby in case the other fails. When the operator has selected the recirculating pump to be used, he closes the drain valve and opens the suction and discharge valves on that pump. He also makes sure that those same valves are closed on the other pump. This is known as lining up the valves. Next, he starts the pump he's chosen for a moment and then stops it. This is to make sure that the pump is supplied with electric power and will start when needed. He follows this procedure each time he selects a pump during the pre-startup checks. The next step is to close the steam trap drain under the reboiler. This prevents the steam that is applied to the reboiler from escaping. Then he opens the steam supply valve to the reboiler. Once this is done, the reboiler is ready to receive the steam used to reheat the bottoms product. Let's go back to the graphics board now and briefly review the steps we've covered so far. To begin the pre-startup checks, the outside operator checked to make sure the overhead product recovery tank drain was closed. Then he selected the recirculating pump to be used by first lining up the valves and then checking to make sure the pump operated properly. After that, he closed the steam trap drain under the reboiler and opened the reboiler steam supply valve. In the next pre-startup check, the outside operator selects a reflux pump. As before, he lines up its valves and then checks to make sure it has electrical power. Then he selects a feed tank pump, following the same procedure he used for the recirculating pump and the reflux pump. Since the outside operator has readied a feed tank pump, the inside operator needs to make sure that there's a sufficient level of mixture in the feed tank. If there isn't enough mixture, the tank could run dry during the distillation process. To check the level in the tank, the inside operator looks at the level indicator on the control board. If the level is low, he'll have the outside operator add more feed mixture. Next, the outside operator opens the steam supply valve to the preheater. This will allow the inside operator to control the steam going to the preheater with the preheater temperature controller when the preheater is put into operation. Before we go on, let's go back to the graphics board again and review the last few checks we just saw. First, the outside operator selected two pumps, the reflux pump and the feed tank pump. Then the inside operator made sure there was enough mixture in the feed tank to begin the distillation process. After that, the outside operator opened the steam supply valve to the preheater. The next thing the outside operator does is open the valve that allows the cooling water to be sent to the condenser. Then the outside operator opens the valves that allow cooling water to flow to the vacuum system condensers. Next, the inside operator checks the hot well level at the control board. A hot well is a tank that receives water or condensate from a vacuum jet system. The liquid level in the hot well is important because it acts as a water seal to prevent air from being sucked back into the vacuum system. If the hot well level is low, he'll tell the outside operator to add water. However, the level is fine, so no water needs to be added. The inside operator now checks with the outside man to make sure that the outside checks are complete. When they are, the pre-startup checks are complete. With the completion of the pre-startup checks, the men have made certain that all the necessary equipment is available for use and all the valves are properly lined up. The system is ready to be started. When we come back, we'll look at the rest of the startup procedure. We'll also see what problems might arise during startup and what can be done about them. In the meantime, read the material in the text and answer the questions. In the first part of this program, we took a look at a series of pre-startup checks. During these checks, the operators made sure that all the equipment necessary for startup was ready for operation. Now we're ready to continue the startup procedure. The rest of the startup procedure can be divided into two stages. In the first stage, the operators need to supply the column with feed mixture, apply heat to start the separation process, and adjust the column temperatures until they meet the required specifications. In the second stage, the feed mixture is fed continuously to the column while the overhead and bottoms products are taken off. Before the first stage of startup, an additional safety precaution could be required. Purging the column would be required if the feed mixture were combustible. The primary purpose of purging is to remove or displace the oxygen contained in the column. Purging is typically done with either steam, nitrogen, or carbon dioxide prior to introducing feed to the column. The feed in this particular system is not combustible, so the operators proceed to the first stage. To begin the first stage of the startup procedure, the outside operator starts the feed pump. While he does that, the inside operator moves the set point on the feed line flow controller from 0 to a specified rate. By adjusting the flow controller, he's opening the feed line valve, which allows the column to start to fill with feed mixture. The inside operator monitors a level indicator, and when the specified level is reached, he stops the flow by setting the flow controller to 0. This closes the feed line valve. Then the outside operator turns off the feed pump to prevent the pump from overheating, since no mixture will be flowing through it. Our particular system is operated at a partial vacuum. This is done so that the mixture will boil at a lower temperature, because the temperatures required to boil the mixture at atmospheric pressure would decompose the bottom product. To start up the vacuum system, the outside operator opens the steam jet valves. In this system, the valve to jet number 2, which is the jet farther from the column, is opened first. The steam jets have to be opened slowly to allow the system to warm up. This prevents damage to the equipment from rapid thermal expansion. He lets jet number 2 run for a while to draw most of the air out of the column. This jet by itself will not create a sufficient vacuum in the column. The inside operator monitors the vacuum in the column. When the vacuum is as high as it can get with only one jet, he has the outside operator open the valve to jet number 1, which further increases the vacuum. Once both steam jets are open, the inside operator allows the column vacuum to build up to the required specification. In the next step, the outside operator starts the recirculating pump at the bottom of the column. This pump recirculates the mixture from the bottom of the column through the reboiler and back into the column. Starting up the pump lowers the level of liquid in the column. Therefore, the inside operator monitors the column level indicator as the pump is started. When the level starts to drop, the inside operator tells the outside operator to start the feed pump. Now, the inside operator can add mixture to the column when it's needed. Once there is mixture circulating through the reboiler, heat can be applied to the reboiler. To do this, the inside operator manually adjusts a temperature controller which opens a valve that allows steam to go to the reboiler. Now, since the reboiler is heating up the mixture, some of the mixture vaporizes when it's recirculated back into the column. This means that the level at the bottom of the column will drop again. Therefore, the inside operator adjusts the flow of feed mixture into the column to keep the level the same. He may need to adjust the feed several times to keep the level constant. As the mixture in the column vaporizes, this vapor rises to the top of the column, where it's routed to the condenser. In the condenser, the vapor is cooled and returned to a liquid state. Part of this liquid will be sent back to the column as reflux. The inside operator monitors the reflux level in the condenser leg. As soon as the level indicator shows that reflux is accumulating, he tells the outside operator to start the reflux pump. At the same time, he sets the reflux flow control valve to a flow rate specified by the system operating guidelines. The inside operator also sets the level controller on the condenser leg to the level prescribed by this system's startup procedure and places it in automatic. Once the overhead product in the condenser leg reaches that prescribed level, the level controller will automatically open the overhead product takeoff valve. At this point in the startup procedure, vapor is rising up the column, and at the same time, liquid is flowing down the column. Each affects the temperature in the column. The rising vapor increases the temperature, and the falling liquid decreases it. For the system to operate efficiently, the two must be balanced so that required temperatures are maintained. There are temperature sensors located at various points along the column. These sensors enable the inside operator to closely monitor the temperatures within the column. During startup, as well as during normal operation, the operator controls the temperature at the top of the column by adjusting the reflux flow controller. This controller regulates the amount of reflux going back into the column. He also regulates the flow of steam to the reboiler. This controls the boil-up rate. That is, the amount of vapors rising up the column. He uses a temperature controller to adjust the steam flow and control the boil-up rate. Both the reflux and the boil-up rate may need to be adjusted several times until the column temperatures are within specifications. At this point, we've reached the second stage of the startup procedure. It's now possible to begin taking off overhead and bottoms products. Once product takeoff has begun, the column will be fed continuously. Ordinarily, overhead and bottoms products don't reach the desired levels of purity at the same time. Whichever product reaches that level of purity first is taken off first. In this process, the overhead product is taken off first. Therefore, to prepare for overhead product takeoff, the outside operator opens a valve in the overhead takeoff line. This valve must be opened manually before overhead product can be sent to the overhead product recovery tank. The overhead product takeoff valve is controlled automatically by the level of product in the condenser leg. The inside operator has already set the level controller on the condenser leg to the value prescribed by the system startup procedure. When the level in the condenser leg gets high enough, the valve opens automatically and the overhead product is pumped to the overhead product recovery tank. The column's bottom temperature and pressure will indicate the right time to begin bottoms takeoff. Therefore, the inside operator will monitor both. To begin bottoms takeoff, the inside operator sets the bottoms takeoff flow controller to a flow rate specified in the system operating guidelines. Now that there is a steady flow of product out of the column has to be fed continuously. Once continuous feed begins, the feed preheater is started up. Applying steam to the preheater before a continuous feed is begun could damage the preheater. This is because the excess heat won't be absorbed by the small amount of liquid in the preheater tubes. This would cause the mixture to decompose and coat the tubes. Therefore, the preheater is started up only after the mixture is being fed without interruption. To start up the preheater, the inside operator sets the preheater temperature controller to the specified temperature. When the preheater is at the correct temperature, the mixture is being fed continuously and the two products are being taken off continuously. The startup procedure is complete. The column is now in operation. As it does most of the time, this startup came off without any problems. However, sometimes problems can occur, and you should know how to deal with them. Let's take a look at some of the things that can happen during startup. Generally, the biggest problem in a vacuum column like this is a leak in the vacuum system. Any change in the vacuum will cause a change in the temperatures and pressures in the column. Such changes could greatly reduce the efficiency of the system or even stop the distillation process completely. If this happens, the system may have to be shut down until the leak has been located and repaired. Another problem might be the buildup of residue in the lines that carry either mixture or products. Such a buildup could block the lines. If this takes place, the blocked line will need to be cleaned out. Finally, one of the instruments used to monitor or control part of the distillation process could fail. This kind of problem may not be immediately obvious, but as operators gain experience with their systems, they learn what kind of readings they should expect. When an instrument reading seems unusual or wrong and everything else appears normal, maintenance should be called to thoroughly check out the instrument. Now, in this part of the program, we've taken a look at the procedure used to start up a distillation column. Of course, as I mentioned earlier, the procedure we've shown you is the one we use here. At other facilities, the procedure may be different. In the next part of the program, we'll be looking at some of the things that can affect the operation of the column once the startup is complete. In the meantime, read the material in the text and answer the questions. When you're ready, we'll continue. Earlier in this program, we took a look at the startup procedure for a typical distillation system. Proper operation of the distillation system depends on maintaining the equilibrium between the rising vapor and the falling liquid in the column. In this part of the program, we're going to look at two aspects of the system that significantly affect this equilibrium: the feed rate and the operation of the reboiler. We'll also see what can happen in a distillation system when this equilibrium is upset. Right now, let's start with the feed rate. The feed rate is the rate at which the mixture is pumped into the column. Typically, it's measured in gallons per minute. When a distillation system is designed, the ideal feed rate for that system is determined mathematically. This ideal feed rate is expressed within a certain range. It's important for the system to operate within that range. This ensures that the distillation process will be efficient and economical as possible. The way feed rates are regulated can vary from system to system. In this system, a flow controller is located on the feed line leading to the column. This device senses the rate of flow and compares it to a preset value or set point, which provides the ideal amount of feed to be supplied to the column. If necessary, it sends a correcting signal to the flow control valve, which opens or closes to keep the flow of mixture within the desired range. Although this type of control causes very slight fluctuations in the feed rate, these fluctuations are to be expected. Large variations, however, can cause significant changes in column temperatures and pressures. When such changes occur, the column can't produce its products at an efficient rate. In addition to a reduction in efficiency, large variations in the feed rate can cause other problems as well. Let's take a look at a few examples. When too much feed mixture is pumped into the column, the result is known as overloading. This can lead to flooding. Flooding occurs when the large amount of mixture flowing down the column prevents the vapors from rising up to the top. When a column floods, the bottoms and overhead products may become contaminated with each other. In addition, severe flooding may damage the internal structure of the column, making it necessary to shut down the column for repairs. Other problems can occur if there's too little feed mixture going into the column. When this happens, the level of mixture at the bottom of the column falls. If it falls too far, there won't be enough mixture recirculating through the reboiler and back into the column to maintain the proper temperature at the bottom of the column. The column temperatures and pressures will drop, and the entire process could come to a stop. Variations in the feed rate can sometimes be caused by mechanical problems. Two examples of this are plugged lines and instrument failures. Occasionally, feed lines can become blocked with residue. When this occurs, the lines will have to be cleaned out before the process can continue. When an instrument fails, it may transmit wrong information or no information at all. If this happens, it may be necessary to manually control the feed rate until the instrument is repaired. For the last few minutes, we've been looking at some of the ways that feed rates affect column equilibrium. Now let's see how the operation of the reboiler can affect this equilibrium. When the column is in full operation, the reboiler provides the majority of the heat used to vaporize the mixture. The reboiler not only supplies heat to the column, it also vaporizes any overhead product that may have come down the column. This means that the reboiler plays an important role in maintaining column equilibrium. Let's take a closer look at this operation. The reboiler is heated by steam. The amount of steam being fed to the reboiler is dictated by the temperature in the column. A temperature controller that has a temperature sensor located in the column will increase the flow of steam to the reboiler if the column temperature is too low, or decrease the flow if the temperature is too high. The amount of steam going to the reboiler increases or decreases the column's boil-up rate. The boil-up rate affects column equilibrium by increasing or decreasing the amount of vapors going up the column. It's important to remember that the reboiler should be full of mixture and recirculating properly before steam is applied. This prevents the mixture from overheating, decomposing, and baking onto the tubes of the reboiler. Now, when steam is applied to the reboiler, it should be done gradually. If the reboiler temperature is increased too rapidly, the heat could damage the reboiler. Also, the reboiler initially contains both parts of the feed mixture. If steam is applied too rapidly, the lower boiling part of the mixture will boil and shoot up the column too fast, possibly damaging the internal structures of the column. And finally, the reboiler temperature could overshoot the desired value and take a long time to recover. Sometimes mechanical problems can affect the reboiler. Such problems could include blockages in the product line and leaks in the steam lines inside the reboiler. When any such problems occur, they should be taken care of as soon as possible. Whenever any change is made to the temperature of the reboiler, it should be made in small increments. Any sudden or large change may upset the equilibrium between vapor and liquid in the column. Once this equilibrium is upset, it's difficult and time-consuming to return the column to a normal operation. In this part of the program, we've looked at both the feed rate and the operation of the reboiler. We've seen that both can affect the efficiency of the distillation process by altering the balance between the rising vapors and the falling liquid in a distillation column. When we return, we'll look at the reflux system. We'll see how the reflux ratio, that is, the amount of reflux returned to the column, can affect column equilibrium. In the meantime, read the material in the text and answer the questions. When you're ready, we'll go on. The efficiency of a distillation column depends on how well the equilibrium of the rising vapors and falling liquid is controlled. In the last part of the program, we looked at two of the factors that contribute to column equilibrium: feed rate and reboiler temperature. In this part of the program, we're going to see how reflux affects the efficiency of a column. As you know, reflux is the overhead product that is pumped back into the column after it's been condensed. When the column is being started up, there is no liquid at the top of the column, and all the overhead product is returned to the column as reflux. In this way, there will be enough liquid at the top of the column to ensure vapor-liquid contact. Once the column is in full operation, a portion of the overhead liquid is taken off as overhead product. The rest of the liquid is returned to the column as reflux. This reflux serves two main purposes: to maintain vapor-liquid contact and to keep the top of the column at a specified temperature. The amount of overhead product taken off compared to the amount returned to the column is the reflux ratio. For example, if 6 times as much liquid is returned as is taken off, that's a 6-to-1 reflux ratio. A reflux ratio like 6-to-1 is generally considered a high ratio. High reflux ratios mean that a great deal of liquid is returned to the column. On the other hand, a 2-to-1 reflux ratio is considered a low ratio. The reflux ratio to be used in a column is determined by the system engineers. It depends primarily on the mixture to be distilled and the design of the column. A mixture that is hard to separate, one whose components have boiling points that are close together, usually requires a high reflux ratio. A mixture whose components have boiling points that are further apart is easier to separate. This kind of mixture will normally require a lower reflux ratio. The reflux ratio used will also depend on the design of the distillation column. A tall column with many trays will usually require a low reflux ratio because more trays allow for more vapor-liquid contact. On the other hand, a short column with fewer trays will usually require a high reflux ratio because fewer trays means less vapor-liquid contact. Earlier in the program, we saw that during initial column startup, all the overhead liquid is returned to the column as reflux. This reflux is necessary to start the vapor-liquid contact in the column. However, when the column is operating normally, it produces more overhead product than is necessary for reflux. This excess overhead collects in the condenser leg. A level controller monitors the level of liquid in the leg. When that level reaches a predetermined point, the controller opens the overhead product recovery valve, which allows a portion of the excess liquid to flow to the overhead product recovery tank. The amount the reflux flow valve is opened determines the rate of reflux returning to the column. This rate is specified by operating procedures. If the valve isn't opened according to operating procedures, the reflux rate may either be too high or too low. Let's see what could happen if the reflux rate isn't what it should be. When the reflux rate is too high, too much liquid is flowing down the column. The liquid blocks the vapors, preventing them from rising up the column as they should. This could cause the column to flood. In addition, the excess reflux cools the top of the column too much. When this happens, not enough top liquid vaporizes. When the reflux rate is too low, there isn't enough reflux going back to the column to keep the top of the column cool enough. When the upper part of the column gets too hot, the bottom's product vapors rise too far up the column. These vapors mix with the overhead product vapors, contaminating them. It's easy to see, then, that the reflux rate is important to the proper operation of the distillation column. In this part of the program, we've seen what reflux is and how the reflux ratio for a particular column is determined. We've also seen what the effects of a too high or too low reflux rate are on the operation of a column. Now would be a good time to review the material in the text and answer the questions. When you're ready, we'll go on. So far in this program, we've seen the proper startup procedure for a distillation system. We've also taken a look at some of the factors that are important in keeping the column operating efficiently. Now we'll take a look at what can happen when a distillation system is called on to produce a product at the upper limit of its designed operating range. For example, the operator may receive a telephone call telling him to step up production. It'll be up to him to make sure that adjustments are made to produce a larger volume of product. These adjustments involve gradually increasing the feed rate of mixture going into the column, increasing the top and bottom takeoff rates, and increasing heat to the reboiler. In addition, he may also increase the reflux rate. These adjustments shouldn't create problems if the column is working well within its operating range. However, if the column is working close to the maximum limit of its range, problems can occur if the column is not being closely monitored. In this part of the program, we'll be looking at some of the problems that can occur while a column is operating close to the maximum limit of its range. The first of these problems is overloading. Overloading occurs when the flow of liquid down the column is so great that it starts to block vapor rising up the column. This can be due to a number of causes. For example, feeding too much mixture into a column can cause overloading. The excess mixture entering the column increases the hydrostatic pressure across the trays, blocking the rising vapors. As you may recall, hydrostatic pressure depends on the height of a liquid. If this height increases, so does the hydrostatic pressure. This increased pressure may be enough to block the rising vapors. Too much reflux being pumped into a column can also cause overloading by altering the hydrostatic pressure in the column, blocking the rising vapors. If this is allowed to continue, two other problems, flooding and eventually puking, may occur. As we've seen earlier, flooding occurs when liquid flowing down the column prevents vapor from rising up the column. When an overloaded column first begins to flood, the flooding is generally limited to a small section of the column. This is known as local flooding. If flooding is allowed to continue, it will eventually involve the entire column. This is known as overall flooding. Flooding can also lead to a different problem, puking. In puking, the pressure of the rising vapor in the column gets so great that it actually forces part of the liquid up to the next level and possibly out of the column. Occasionally, this can happen with enough force to cause serious damage to the internal structure of the column. In order to avoid this kind of damage, it's important to be aware of any indications that the column is being overloaded. There are a number of ways to tell if overloading is taking place. For example, if the pressure at the bottom of the column begins to rise and then surge up and down, this could be one warning sign. A further sign could be a sudden, rapid fluctuation in the temperatures in the column. Overloading can be indicated by surges of takeoff at the top of the column. Whenever these warning signs occur, certain preventive measures should be taken to assure that the overloading doesn't develop into flooding and puking. Generally, one of the first things to do to prevent overloading is to lower the reflux rate. This reduces the amount of liquid flowing down the column. When the reflux rate is lowered, the amount of overhead product being taken off increases. This reduces the overall amount of liquid in the column. Removing the excess liquid in the column may be enough to cure the problem. However, in some cases, such as when local flooding occurs, it may be necessary to reduce the feed rate as well as the reflux rate. This further reduces the amount of liquid entering the column and helps to reduce the pressure in the column. In addition, the temperature of the column can be lowered by reducing the steam flow to the reboiler. This reduces the amount of vapor in the column. In extreme cases, such as overall flooding, it may be necessary to shut the column down altogether. This allows the liquid to drain down to the lower section of the column. If this doesn't make the level in the lower section too high, the column can then be restarted. If the level is too high, some of the liquid will have to be drained out of the column before it can be restarted. The examples of flooding we've just looked at were all caused by changes in the amount of liquid going into the column. But sometimes flooding can occur because of some mechanical problem which results in a blockage of vapors or liquid. For example, the buildup of scale deposits on bubble caps or on the packing in columns can restrict the flow of vapor in a column. The same thing can happen if a tray or a part of a tray breaks loose and falls onto the tray below. In columns that use packing instead of trays, the packing itself may become damaged and restrict the flow of vapors or liquid. Reducing the amount of liquid going back to the column will help to control the flooding caused by these mechanical problems. Eventually, however, the column will have to be shut down so that the problem can be repaired. In this part of the program, we've looked at the procedures involved in increasing the production of a column and some of the problems that can occur when a distillation column is run at the upper limit of its designed operating range. We saw that a column can be overloaded by too high a reflux rate or too high a feed rate. We also saw that if overloading is allowed to continue, it will lead to flooding. If local flooding in one area of the column isn't stopped, it can lead to overall flooding of the entire column. When this happens, the overhead and bottoms products can become contaminated with each other. In addition, the internal structure of the column can be damaged. We also saw that flooding can occur because of a mechanical problem that restricts or blocks the flow of liquid and vapor within the column. Finally, we looked at some of the ways that overloading or local flooding can be controlled so that the column can continue to operate. Sometimes, however, the column does have to be shut down. In the next part of the program, we'll be looking at the procedure for shutting down a distillation system. In the meantime, read the material in the text and answer the questions. When you're ready, we'll continue. In the last part of the program, we discussed some of the problems that can occur while a distillation column is in operation. Problems such as overloading and flooding. We saw that these problems can sometimes be remedied by adjusting the reflux rate or the feed rate. We also saw that some problems may require the column to be shut down so that repairs can be made. Well, in this part of the program, we'll look at the procedure for shutting down a distillation system. We'll examine three different shutdown procedures. First, we'll see the procedure for a short-term shutdown. In general, a short-term shutdown is one in which the system is expected to resume operation shortly. Next, we'll see the procedure for a long-term shutdown. Unlike a short-term shutdown, a long-term shutdown can be for an indefinite period of time. The system may need to be repaired, or the particular products it produces may no longer be needed. Finally, we'll look at the procedure for an emergency shutdown. The column may have to be shut down for an emergency, such as one caused by a mechanical problem or a power failure. It's important to follow shutdown procedures carefully. If a column is shut down improperly, there probably won't be an indication of a problem at that time. However, when the column is restarted, all kinds of problems could occur. For example, if the vacuum jets are shut down improperly, water from the vacuum condensers could be drawn back into the column when the column is restarted. This could contaminate the distillation products. Well, let's take a look at the short-term shutdown procedure. The basic goal of a short-term shutdown is to stop feed to the column and stop the overhead and bottoms product takeoff. The majority of the equipment is kept in operation so that the system can be restarted quickly. In the first step, the inside operator shuts off the steam to the preheater by setting the preheater temperature controller to 0. This removes heat from the feed mixture. Next, the inside operator stops the flow of feed mixture to the column. He does this by resetting the feed flow controller to 0. At the same time, the outside operator shuts off the feed pump. This isolates the feed system and prevents any more mixture from entering the column. Now that the flow of feed has been stopped, the level of overhead product in the condenser leg will drop because overhead product is still being taken off. When this happens, the condenser leg level controller will automatically close the overhead takeoff valve. The column has now been put on total reflux. Meanwhile, the inside operator moves the set point of the bottom's takeoff flow controller to 0. This stops the removal of the bottom product from the column. He will also reduce steam to the reboiler because there will be a reduced load on the column with no feed going into it. Once the column is on total reflux, the inside operator monitors the level in the condenser leg. He adjusts the amount of steam going to the reboiler to keep that level constant. At this point, the column is now in a short-term shutdown. Let's take a look at the graphics board and see what parts of the system are affected by the short-term shutdown. In a short-term shutdown, only the parts of the system that supply mixture to or remove product from the column are shut down. The rest of the system remains in operating status, ready to resume production when the column is restarted. In a long-term shutdown, however, all the equipment is shut down. This is because there is no expectation of restarting the column at any time in the near future. To begin the long-term shutdown, the inside operator shuts off the steam to the preheater by resetting the preheater temperature controller to 0. Next, the inside operator resets the feed flow controller to 0, which shuts off the flow of mixture to the column. Next, the outside operator shuts off the feed pump. The inside operator sets the temperature controller to 0. This closes the reboiler steam valve. This stops heat going to the column and halts the distillation process. The recirculating pump at the bottom of the column is left on for a short while to help cool down the mixture. Meanwhile, the inside operator moves the set point of the bottom's takeoff flow controller to 0. Once heat to the column is stopped and the column cools down, the vapor will condense, flowing down the column and mixing with the bottom's product. Resetting the bottom's takeoff flow controller to 0 stops removal of the bottom's product and prevents any contaminated product from mixing with the pure bottom's product. To shut down the reflux system, the inside operator does two things. First, he resets the reflux flow controller to 0. This prevents any top product from returning to the column. Then, he resets the condenser leg level controller. This allows the product that has collected in the leg to drain to the overhead product recovery tank. When the condenser leg has drained, the outside operator shuts off the reflux pump. The next step is to shut down the vacuum system. To do this, the outside operator opens a bleed valve in the vacuum line. This breaks the vacuum by allowing an inert gas to enter the column and enables the system to return to atmospheric pressure. An inert gas, such as nitrogen, is used instead of air to prevent the possibility of creating an explosive atmosphere in the column. Then the outside operator shuts off the steam jets. Jet number 1 first, then jet number 2. When the vacuum system has been shut down, the column can return to atmospheric pressure. Once the column has returned to atmospheric pressure, the outside operator shuts off the recirculating pump at the bottom of the column. By this time, the mixture has cooled enough and further recirculation is not necessary. The final step in the long-term shutdown for this system is to drain the column and the reboiler. This is done because if the outside temperature drops below freezing, the liquid might freeze in the equipment, causing damage. In addition, the liquid might deposit a residue that will have to be removed before the system can be restarted. Typically, the contents of the column and the reboiler go to a separate holding tank set aside for that purpose. This long-term procedure differs from the short-term procedure in that all the equipment is shut down and the materials are removed from the system. The final shutdown procedure we'll look at is the emergency shutdown. There are several types of emergencies that would require shutting down the system. For instance, there might be a boiler failure causing a loss of steam to the reboiler or the vacuum system. Another reason would be a failure in the cooling tower that provides chilled water for the condenser. If this happens, the top of the column will not be kept cool enough to prevent the bottoms product from vaporizing and contaminating the overhead product. Finally, there might be an electrical failure in the system. Although there are a few extra steps taken, the emergency shutdown procedure is similar in purpose to the short-term shutdown. That is, the system is expected to return to operation once the emergency has been dealt with. In the first step, the inside operator shuts off the steam to the preheater, and then he shuts off the feed to the column. Then the outside operator shuts off the feed pump. Next, the inside operator moves the set point of the bottoms takeoff flow controller to 0. This stops removal of bottoms product from the column. The inside operator then turns off the reflux system by setting the reflux flow controller to 0. Then the inside operator sets the temperature controller to 0. This shuts off the steam to the reboiler. Now that the flow of feed has been stopped, the level of overhead product in the condenser leg will drop. When this happens, the condenser leg level controller will automatically close the overhead product takeoff valve. The outside operator then shuts off the reflux pump. Finally, the outside operator brakes the vacuum and shuts off the steam jets. He does this because in an emergency, the system may lose steam. Shutting off the vacuum system prevents water from being drawn back into the column from the steam jet condensers. Now let's look at the board again and see how the emergency shutdown procedure affects the system. In this procedure, the feed of mixture to the column and the takeoff of products have been stopped. In addition, the steam used to heat the reboiler has been shut off, and the vacuum system has been shut down. Although the column is almost completely shut down, it can still be restarted more easily than it could if a long-term shutdown had been performed, because there is mixture in the column which is being recirculated. In this program, we've taken a detailed look at the operation of a distillation system. We started by seeing the startup procedure for a vacuum distillation column. Next, we saw how to monitor the operation of the column and how to prevent problems like overloading and flooding from occurring. We also saw what to do if these problems do occur. Finally, we looked at procedures for shutting down the distillation column in 3 different circumstances. The specific procedures used in your facility may differ somewhat from those you've seen here. However, the general principles for starting up a column, maintaining its operation, and shutting it down should be the same anywhere. Make sure you understand the information we've presented here. Read the material in the text and answer the questions. If you understand the procedures you've seen in this program, you'll be able to do a better job where you work.